Welcome to lecture series on Introduction to Nanotechnology. In this lecture series, we are going to discuss about the salient parameters of nanoscience and nanotechnology, including quantum well, quantum wires, quantum dots and fullerenes and so on. So, the title of this episode is Introduction to Nanotechnology. So, what do you mean by nanotechnology? So, as per the definition of nanotechnology or the branch of nanotechnology that deals with the dimensions of less than 100 nanometers. In recent years, nanotechnology has become one of the forefront subjects in the field of physics, chemistry, engineering and biology. In other words, nanotechnology is an interdisciplinary subject that deals with the dimensions of less than 100 nanometers. So, what do you mean by the dimension of less than 100 nanometers? You take a particle, the particle size should be the size less than 100 nanometers, that is 1 nanometer is approximately equal to 10 power minus 9 meter. So, you think or imagine what is the dimension of 100 nanometers. Therefore, nanotechnology is the branch of technology that deals with the dimension of less than 100 nanometers. So, here in this nanotechnology, you manipulate the individual atoms and molecules. So, when you try to manipulate the individual atoms and molecules in the regime of less than 100 nanometers, a new kind of technology arises, and such a kind of technology you call it as nanotechnology. Or in other words, we can define nanotechnology is a process of separation, consolidation and deformation of materials by one atom or molecule. So, this was the statement given by a famous scientist Noria Taniguchi. Or we can define a nanotechnology mainly consists of the processes of separation, consolidation and deformation of materials by one atom or one molecule. So, what is a nanometer? So, normally we come across meter, centimeter and decimeter. We know that 100 centimeter is 1 meter, and similarly a nanometer is a unit of length in the metric system. So, which is equivalent to 1 billionth of a meter. What do you mean by 1 billionth? 1 billionth is nothing but it is 10 power minus 9 meter. Therefore, we can say 1 nanometer is equal to 10 power minus 9 meter. Therefore, technology is the making, usage and knowledge of tools, machines and techniques in order to solve a problem or perform a specific function. So, these are the fathers of nanotechnology. So, this scientist name is Dr. Richard Feynman, and he introduced a concept. That concept is called, the first ever concept was presented in the year 1959 by a famous professor. His name is Dr. Richard Feynman, in the lecture of There is Plenty of Room at the Bottom. And this scientist, Dr. Richard Feynman, was awarded the Nobel Prize in Physics in the year 1965. And similarly, this term nanotechnology was coined by a scientist Norio Taniguchi in the year 1974. So, he is the scientist. The scientist name is Professor Norio Taniguchi. And now one more scientist is there. His name is Dr. Eric Drexler, and he gives the idea of molecular machinery manufacturing and computation in the year 1980s. And this is the diagram of the ancient Catholic Church in Rome, where the church dates back to 1000 years ago. And in the church walls, paintings were drawn, which is 1000 years ago ancient, and we can see the paintings are of different size gold nanoparticles, and they were used for produces stainless glass windows. In similarly, 2000 years ago, sulfide nanocrystals were used by the Greek and Roman for the dyeing of the air. And this cup name is Lycurgus cup. This cup was manufactured in the year 4th century by the Romans, and the glass contains, that is, the cup contains the glass which contains gold silver alloyed nanoparticles, which are distributed in such a way to make the glass look green in reflected light. But whenever a light passes through this cup, it reveals a brilliant red color. Without passing the light, the color is shown in light blue, but when a light is passed through the cup shows a brilliant red in color. And this is a tabular column showing the nanometer scale, and the scale of the things nanometers and more. And we can see these are the nanometers, and these are the things man made. And when you compare these things, we can easily achieve this. For example, we can say it is 1 nanometer, it ranges to 0.1 millimeter. Therefore, there are two kinds of world. One is a nano world, another is a micro world. And the nano world starts from 0.1 millimeter to 10 power minus 9 meter, and whereas the micro world starts from 10 power minus 4 meter to 10 power 6 meter. And we can describe the colors of nanomaterial also. So, thin films are made of nanoparticles smaller than 400 nanometers that produces iridescent rainbow like colors when light strikes them. And this iridescent colors change when you look at the object from different angles. So, when you see an object from different angles, the colors will be different at different angles. And the approach of nanotechnology has two approaches. One, you call it as a top down method. The other method you call it as bottom up method. So, first we will discuss what is a top down method. This M and P denotes known as metal nanoparticles. So, in the top down method, there are three processes, or there are three steps, where you have a bulk metal, a powder, and finally you produce a metal nanoparticles. That is, you take a bulk metal, say for example, the bulk metal may be aluminum, gold, silver or copper, and you convert this bulk metal into a powder, and after converting this into a powder, you finally produce to form a metal nanoparticles which is in the dimension of 10 power minus 9 meter. Therefore, in this top down approach, there are three steps. One is the product of bulk metal, next conversion of bulk metal to powder, next is conversion of powder to metal nanoparticles. And similarly, the reverse of top down method, you call it as bottom up method. In this bottom up method, there are also three steps. The first step is it contains many number of atoms, where the many number of atoms combine to form clusters, and these clusters form the metal nanoparticles in the range 10 power minus 9 nanometer. Therefore, the approach of nanotechnology has two processes. The first process you call it as a top down method, and the second process you call it as a bottom up method. And in the top down method, we should remember an important parameter known as photolithography. Photo means light, litho means it is writing, and graphy means also it is writing. Therefore, this photolithography uses light, that is, it uses an ultraviolet light or deep ultraviolet light or extreme ultraviolet light or X-ray to expose a layer of radiation sensitive through a mask polymer. The mask polymer must be photoresistance, and this is the step by step for preparing photolithography. Therefore, this photolithography uses light to expose a layer of radiation sensitive through masked polymer, that is, it is a photoresistant polymer. So, the first process is preparation of vapor, and the second step is you apply a photoresist, and the third step is align photomask, and the fourth step is exposed to UV light, and the fifth step is to develop and to remove photoresist exposed to UV light. The next step is etch exposed oxide, and the next step is remove remaining photoresist. Therefore, how many steps are there? There are 1, 2, 3, 4, 5, 6 and 7, and these 7 steps are required for a photolithography. So, I once again repeat, the first step is preparation of vapor, and the second step is you apply a photoresist material, and the third step is you align a photomask, and the fourth step is to expose this photomask to ultraviolet light, and the next step is to develop and remove photoresistant material which is exposed to ultraviolet light, and if there are any unwanted things, you etch them in exposed oxide, and finally you remove the remaining photoresistant material, and you finally get the substrate nano product. Other important thing is scanning lithography. So, in the last slide we have seen about photolithography, and in this slide we are going to discuss about scanning lithography. So, what is the difference between photolithography and scanning lithography? In a scanning lithography, energetic particles such as electrons and ions can be used to pattern appropriate resist films, leading to futures with nanometers resolution. And recently established technology uses the nanometer scanning probes for patterning resist films, and it is therefore referred as scanning probe lithography. So, the abbreviation for scanning probe lithography is SPL, and the scanning lithography uses high energetic particles such as electrons and ions to pattern the appropriate figure. And the next lithography you call it as E-beam lithography, and the electron beam lithography or electron beam direct right lithography scans a focused beam of electrons on a surface. You take a surface, on the surface the electron scans the surface covered with an electron sensitive film or resist to draw custom shapes. So, you can change the solubility of the resist and subsequent selective removal of material by immersion in a solvent. In this electron beam lithography, the size of approximately 10 nanometer resolution can be achieved, and this is a schematic diagram for bottom up method. The best example for a bottom up method is chemical vapor deposition, and in the chemical vapor deposition we need to have a precursor. These precursor gases are delivered into the reaction chamber at approximately ambient temperatures. So, as they pass over or come into contact with the heated substrate, they react or decompose, forming a solid phase which and are deposited onto the substrate. The substrate temperature is critical and it can influence what reactions will take place. Therefore, in this chemical vapor deposition, what is more important is the substrate temperature and the precursor gases. So, when you have this precursor gases and the substrate temperature, you can easily achieve an important method known as chemical vapor deposition. Therefore, that is we have ordinary lithography and scanning probe lithography, and in the bottom method there is an important technique known as chemical vapor deposition technique, and this is sol gel technologies and their products. So, in the sol gel technologies and their products, we have a solution, that is a sol, and you have a hydrolysis polymerization, and where thereby it can yield metal alkoxide solution, that is a sol, and you have a hydrolysis polymerization, and where thereby it can yield metal alkoxide solutions, and you coat this with zero gel film and you heat this zero gel film and you get this dense film. Similarly, in the sol gel process, you take the sol material and you coat and you will get a wet gel, and with this wet gel you get a zero gel, and with the zero gel you can form dense ceramic. Similarly, in the sol gel you take by precipitation approach and you get the uniform particles, and finally you can obtain from this wet gel you can finally obtain aerogel. Therefore, in this sol gel technique we can produce two types of nanoparticles. Either you can produce in the form of film, or you can produce in the form of zero gel, or you can produce in the form of aerogel. So, what is the necessary for bottom up approach? So, the important condition for bottom up approach, that is there are two kinds of approaches. One is top up and bottom up, or top down or bottom up, and among these two, bottom up approach is served a lot because it has various advantages and it allows smaller geometries than photolithography. And the second advantage is certain structures, say for example, if you take fullerenes or carbon nanotubes and silicon nanowires, you can grow easily by a process called this bottom up process when compared to the top process. And new technologies such as organic semiconductors employ bottom up process to pattern them. And similarly, this bottom up process can make formation of films and structures much easier. And the last advantage is it is more economical than top down approach. Top down approach, cost wise it is very costly when compared to bottom up approach. Therefore, this bottom up approach is more economical and it does not waste material during etching. And this is a schematic diagram to depict the surface area to volume ratio. So, for any synthesis of nanomaterial, whether it is a top down or bottom up approach, the surface area to volume ratio is much be reduced. So, whenever you try to reduce the surface area to volume ratio, the nanomaterial becomes a perfect material. Therefore, in a nanomaterial, the surface, that is the surface of the material or the boundary of the material or the interface of the material plays an important role. And as surface area per mass of a material increases greater amount of the material and it can come into contact with the surroundings material, thus affect the reactivity. So, now let us look at this diagram. When you look at this diagram, the sides are 3 in number, and what will be the surface? The surface is nothing but it is length into breadth, therefore, it is 3 squared into 6. So, 3 square is 9, 9 into 6 is 54. So, the surface is 54, and what is the volume? The volume is length into breadth into height, therefore, it is 3 power 3, and 3 power 3 is nothing but it is 27. And what is the surface to volume ratio? It is 54 by 27. So, it is 27 twice times 54, therefore, the surface to volume ratio is 2. Similarly, you consider this morphology of a surface. Here the surface is 2 in number, 1 and 2, therefore, you have 2 sides. And what is the surface? Since it is length into breadth, therefore, 2 squared into 6, it is 2 square is 2 into 2 is 4 into 6 is 24. Similarly, for volume, it is length into breadth into height, 2 power 3 is 2 into 2 4, 4 2s are it is 8, and the surface to volume ratio is 3. You take this surface morphology, the side is 1, therefore, the surface is 1 squared into 6 that is equal to 6, and the volume is 1. Therefore, the surface to volume ratio is 6. So, when you compare these 3 diagrams, The first diagram has a side 3 as a volume ratio, surface to volume ratio 2. So, for a 3 dimension it is surface to volume ratio is 2, and similarly for a 2 dimension the surface to volume ratio is 3, and similarly for a single dimension the surface to volume ratio is 6. Therefore, as you increase the dimension 1, 2 and 3, what do you see is the surface to volume ratio decreases to a considerable extent, and therefore, based on that we can classify the material into a 0 dimension material, or a 1 dimension material, or a 2 dimension material, or a 3 dimension material. So, therefore, you can classify this nanomaterial into 0 dimension, 1 dimension, 2 dimension, 3 dimension. So, what is a 0 dimension material? That is, we are speaking with respect to nanoparticle alone. Therefore, if the nanoparticles are spherical in size as shown in the diagram, the example of a spherical nanoparticle is the gold nanoparticle. Therefore, the classical example for a 0 dimensional nanoparticle is a gold nanoparticle, and these nanoparticles are spherical in size, and when you see the diameter of these particles will be in the range of 1 to 50 nanometer. Therefore, if any particle, whether it is a gold nanoparticle or a silver nanoparticle or a aluminum nanoparticle, if the dimension of this nanoparticle lie within the range of 1 to 50 nanometer, such a type of material are known as 0 dimensional material. And what do you mean by 1 dimensional material? The classical example for a 1 dimensional material is a carbon nanotube. So, that is, what is a carbon nanotube? Carbon nanotube is a nanomaterial which is completely made up of carbon and carbon alone, and its structural diagram for a carbon nanotube is cylindrical or spherical in tubular in structure. Therefore, the best example for a 1 dimensional nanomaterial is a carbon nanotube, and these materials are long, and these materials are micrometers in length. What is micrometer? It is 10 power minus 6 meter. So, if the materials are in the length of 10 power minus 6 meter, and if the diameter is only a few nanometer, and such a kind of material you call it as 1 dimensional material. Therefore, the best example for a 0 dimensional nanomaterial is a gold nanoparticle or a silver nanoparticle, and for a 1 dimensional nanomaterial it is a carbon nanotube, where the diameter of the carbon nanotube should be only a few nanometers. And what is a 2 dimensional material? So, the best example for a 2 dimensional material is a solar thin film. As you can see in this diagram, a solar thin film is gently wrapped in the fingers, in the hand, and these include different kinds of nanofilms, and this nanofilms may be of coatings or thin film multilayers, and nanosheets or nano walls. Therefore, the 2 dimensional nanomaterial may be of a nanofilm, or it may be of coating, or it may be of thin film multilayers, or it may be of nanosheets or nano walls. Therefore, and the other important thing you should remember is the area of the nanofilms can be large, that is, large in the sense that it may be several square micrometer in length, but the thickness is always in the nanoscale range. And this is the bulk material. It is a 3 dimensional material, and the 3 dimensional material may be the, whereas here there are number of colors are given in this material. The blue color denotes, here the blue color in this diagram denotes cadmium element, and the red color denotes selenium or sulfur, and similarly in the yellow color it denotes zinc and cadmium, and the green color of the nanomaterial denotes sulfur or selenium. And this, that is, you have 3 parts in this 3 dimensional material, because since it is of 3 dimension, you have length, breadth and height, that is, you have a core, shell and a amphibic surface. In the core surface you have cadmium selenide or cadmium sulfide. In the shell surface you have zinc sulfide, cadmium selenide or zinc selenide or cadmium sulfide, and there is a surface known as amphibic surface, and these include bulk materials compressed of individual blocks which are in the nanometer scale of 1 to 100 nanometers. Summarize what we have learned so far in this session. In this session, we discussed about what is nanoscience and what is nanotechnology, and we discussed the fathers of nanotechnology. The fathers of nanotechnology are Richard Feynman, Noria Tanguchi and Dr. Eric Drexler, and we also discussed about some ancient nanomaterials observed in the Catholic churches as paintings, and we discussed about a famous cup known as Lycurgus cup, which belongs to the Roman century in the year 4th century, and we discussed about the nanometer scale and the colors and the approaches of nanotechnology like top down method and bottom up method, and we discussed about photolithography, scanning lithography and e-beam lithography, and we discussed about the salient features of bottom up method, and also we said what is the advantage of bottom up method, and we expressed a few words on surface area to volume ratio. Based on the surface area to volume ratio, we discussed the classification of nanomaterial into 0 dimension, 1 dimension, 2 dimension and 3 dimension nanomaterial. Let me pose you some questions so that you may be able to answer. So, here are the list of questions. The first question for you is, what is nanotechnology? And the second question is, what are the approaches of nanotechnology, and name the 2 approaches of nanotechnology. And the third question is, what do you mean by photolithography, scanning lithography? And the next question for you is, what do you mean by e-beam lithography? Write notes on e-beam lithography. What are 0 dimensional materials, 1 dimensional materials and 2 dimensional materials and 3 dimensional materials? Thank you.